In this lecture, we are going to discuss a very popular topic in modern deep learning, GANs. GAN stands for Generative Adversarial Network. Yann LeCun, who is one of the forefathers of deep learning, described GANs as the most interesting idea in machine learning in the past 10 years. By the way, this is also who the famous LeNet architecture of convolutional neural networks was named after, the CNN from which all other CNNs are based. Ian Goodfellow, the inventor of GANs, is now himself a prominent deep learning researcher. My goal in this lecture is to introduce you to the fundamental theory behind GANs. You'll see that, although they sound complicated, they are nothing but a new and interesting way of combining things we already know how to build. This is a common pattern in deep learning. Neural networks themselves are nothing but a bunch of logistic regressions chained together. CNNs and RNNs are nothing but neural networks with shared weights. I like this approach because deep learning allows us to build tons of cool things with only a few simple tools and some creativity. First, let's discuss what GANs are even used for in the first place, since this may not be immediately obvious. The main use case for GANs is to generate data. 99% of the time, this means generating images. The reason GANs have become so popular is because unlike the models that came before it, GANs are exceptionally good at this. Here are some example images produced by state-of-the-art GANs. Believe it or not, these are not real people, but rather images generated by a computer. One thing you can do, if you want to see a few more examples and observe for yourself the power of GANs, is to check out a few websites that display such examples. One website is thispersondoesnotexist.com. This one is simple. You go to the page and it shows you a randomly generated face. You can refresh the page to see more faces. Another one which I really like is whichfacesreal.com. This one is more like a game. So you're shown two images, and one is real, one is fake, and you have to pick the right one. So check these out for yourself if you want to see more examples of how good GANs are at generating realistic images. Okay, so what's the main idea behind GANs? GANs are a system of two neural networks, each of which has their own objective. The objective of the first neural network is to generate images. The objective of the second neural network is to discriminate between real and fake images. This is all you need to understand how GANs get their name. They are generative because you are generating images. They are adversarial because you have two neural networks which oppose each other in an adversarial manner. They have opposite goals. The goal of the first neural network is to generate images that look real, and the goal of the second neural network is to detect real and fake images. Intuitively, you can think of GANs like a counterfeiter and a shop owner. The counterfeiter goes to the shop and tries to use fake cash to buy an item. The shop owner has to detect whether the cash being given by customers is real or fake. Perhaps at the beginning, both the counterfeiter and the shop owner are not experts at what they do. The counterfeiter is not that good at making fake bills, but the shop owner is also not that good at detecting fake bills. However, once the shop owner learns to detect the fakes, the counterfeiter may then improve on his counterfeit design and trick the shop owner once more. After a while, the shop owner may again realize he is being duped and learn to inspect the bills more carefully to detect these improved fake bills. The cycle continues as the counterfeiter gets better at tricking the shop owner and the shop owner gets better at avoiding being tricked. Of course, these analogies only take us so far. How do we actually build a GAN? Let's recall all the ingredients we need for a basic neural network that we want to train. First, we need a neural network. That much is obvious. Well, in our case, we actually have two neural networks. In order to train the neural network, we need an objective or a loss function. This is the big question with GANs. What is the loss function? But once we have these two things, everything else is nearly trivial. We call model.fit, which does gradient descent, and that's that. Okay, so let's dig a little deeper on what the loss function is. In fact, for GANs, we're going to have two loss functions, one for the generator and one for the discriminator. Let's first look at the discriminator, since that's more in line with what we are used to already. Since the discriminator must be able to tell the difference between real and fake images, this is a binary classification problem. For every input, the discriminator can only predict one of two categories, real or fake. As you know, for binary classification, the correct loss function is the binary cross entropy. What about for the generator? What is the loss function? This is what I call applying creativity to the basic tools that we already know about. Intuitively, the basic idea is this. We have our generator network, and our generator network feeds into our discriminator network. From this perspective, this is just one gigantic neural network. What we can do is, just like with transfer learning, we can freeze the layers in the discriminator so that when we run gradient descent, only the generator network gets trained. Next, and here is the ingenious part, we want the generator to get better at producing real-looking images. And so our loss function will remain the binary cross entropy, except that we are going to switch the labels. In other words, let's say for the discriminator, real is 1 and fake is 0. We're going to pass in fake images, but make the target 1, such that we're encouraging the discriminator to identify these fake images as real. But the discriminator weights are frozen, so they won't change when we do this. Only the generator weights are trained. Here's what the loss would look like, mathematically, if you're interested. Here, all the y-hats are predictions on fake images, since the generator is now the input into the discriminator. Because we always want the target to be 1, we only care about the first half of the binary cross entropy. So essentially, it's just the sum over the log of all the y-hats. Or stated another way, the negative log likelihood of the y-hats. Now that you understand the basics of how GANs work, let's look at some details that will help us in our implementation. We know that neural networks must have both inputs and outputs. For the discriminator, this is easy. The input is an image, and the output is a prediction about whether the input image is real or fake. For the generator, this will be a little strange. We know that the output should be an image because its job is to generate images. But what is its input? In fact, the input to the generator is nothing but noise. What we are going to do is generate noise from a multivariate standard normal, and the generator will learn to map this noise to an image. Mathematically, what we are doing is saying, we have some random vector z, which comes from a standard normal. Let's say it has size d equals 100, although this is a hyperparameter, so you can choose what you like. We call this 100-dimensional space the latent space. In essence, you can think of it as an imaginary space where the generator believes all the images of digits live. So maybe the 1s are over here. All the 7s are right beside it because 7s kind of look like 1s. Near the 7s are the 9s because 9s look like 7s if you draw the loop very small. So you can see how these images kind of morph into one another when they are drawn in different ways. So this latent space maps all the different kinds of images that you can have. And of course, this is a source of confusion for both computers and humans. When an image is right on the boundary between, say, 7 and 1, it's difficult for us to tell what digit it should be. Should it be a 7 or should it be a 1? In any case, what the generator is doing is, it's learning to associate each part of the latent space with different images in a continuous manner. Then later, when we generate images, we're just picking a random part of the space and generating an image from whatever that part of the space represents. You can think of the generator as kind of the reverse of a feature transformer or an embedding. With a feature transformer or an embedding, we're taking an input image or an input text or some other kind of input, and we're mapping it to a vector. But for a generator in a GAN, we're doing the opposite. We start with a vector, and then we map that to an image. As always, it's going to be helpful to look at some pseudocode before we move on to the actual implementation. So here's how it's going to look. So the first step is to load in our dataset. We're going to use MNIST for this example. In future courses, you'll learn about more advanced types of GANs, which will work on more complex types of data. Next, we're going to create our discriminator and generator networks. These are just standard neural networks, some dense layers, some ReLUs, and so forth. The trick is, we're going to have two optimizers. One that optimizes the parameters of the discriminator, and one that optimizes the parameters of the generator. Conceptually, you can imagine that the loss function is always applied to the output of the discriminator only. In either case, we will use the binary cross entropy, but with flipped labels. When we train the discriminator, half of the data will be real images from the dataset, and half of the images will be generated from the generator. These will use the true labels. When we train the generator, we will generate random noise, pass that through the generator, then pass that through the discriminator, and use a flipped label, meaning that we say it's a 1 even though it's really a 0. We can conceptualize this chain of generator and discriminator as a kind of combined model, where only the generator weights our parameters. Although that's not exactly how it will look in code, it's a good conceptual tool. Once we've built our two networks, we're going to run a gradient descent loop as usual. Inside the loop, we're going to train the discriminator and generator in alternating order. In order to train the discriminator, we'll grab a random sample of images from our dataset and a random sample of images from our generator. Then we'll do one iteration of gradient descent by calling discriminator.trainOnBatch. We do this for both the real and fake images. Then for generator training, we'll do the following. First, we'll generate a batch of noise samples. Then we'll call combinedModel.trainOnBatch, passing in the noise and ones for the target, to do one iteration of gradient descent on the generator. After several thousand iterations, our generator should be good enough to produce images that look like the MNIST dataset. As a final note for this lecture, I want to mention that, in terms of model evaluation, we're going to take a bit of a departure from what we normally do. You'll recall that for most models, what we're looking for after training is that the loss goes down and the accuracy goes up. This makes sense if you were doing classification or regression. But now we are no longer doing classification or regression. Remember that in our case, the generator and discriminator are constantly trying to one-up each other. And so what is interesting is that the loss functions for both the generator and discriminator should look just like noise. It should appear that, if you only look at the loss per iteration, that nothing is happening at all. But in fact, something profound is happening. Both the generator and discriminator are improving. You don't see this in the loss per iteration because ideally, both the generator and discriminator are improving at the same rate. Let's now summarize everything you learned in this lecture. First, you learned that GANs are not just a single neural network, but a system of two neural networks, a generator and a discriminator. The discriminator is responsible for telling the difference between real and fake images. The generator is responsible for creating realistic-looking images. Both the generator and discriminator learn in tandem. The loss function for the discriminator is just the binary cross entropy because there are two classes, real and fake. The loss function for the generator is not directly applied to the generator, but rather a combined model where the generator feeds into the discriminator. This allows us to, again, use the binary cross entropy, but there are two important details. First, we freeze the weights of the discriminator so that only the generator is trained. Second, we flip the labels so that images generated by the generator are labeled as real. Next, we learn that the input to the generator is nothing but noise, sampled from the latent space. The latent space is where the encodings for each digit lives. You can think of this as the opposite of a feature transformation or an embedding. An embedding or feature transformation is like a mapping from an input image or an input word or any other kind of input into a single vector. The generator does the opposite. It takes a vector, which lives in the latent space or the embedding space, and produces an image. Lastly, we learn that when training GANs, the loss per iteration should not be informative in the sense that it should not decrease over time, as it does when we are training other models. This is because both the discriminator and the generator should be learning at the same rate, continually helping each other improve.